So in this module we will solve some interesting physical problem with the use of Kummer's function. Before turning to the problem itself, let us introduce or recall for those who know some fundamental problem of elementary quantum mechanics. And this problem is about one-dimensional motion. And imagine that you have a particle which lives in one dimension and is propagating in some potential u of x. So, and the question is, can this potential, if it is very weak, can it create a bound state for the propagating particle? And to characterize the general potential, it's convenient to introduce its typical magnitude, which is minus u naught, and typical spatial scale, which is a. So to be a bit more formal, and for those who are not so well familiar with quantum mechanics, let us recall that this problem is described by Schrödinger equation. And if you don't feel very comfortable with quantum mechanics, don't worry. All what we need to do in the end is to study properties of this differential equation. So this is just a Schrödinger equation for one-dimensional particle. In the end, the physical problem is reduced to the mathematical one, and this mathematical problem is to find solutions of this differential equation which are normalizable, that is, the integral squared is convergent. And this is doesn't happen for arbitrary value of E, but for some discrete set of them, which are called eigen levels of this quantum mechanical problem. And this is a very general problem which can be solved for arbitrary potentials, u of x. And before we proceed to some non-trivial cases, let us see how it works for a very simple situation and derive so-called spectral equation, which we will later use for other potentials. But in the most simple situation, the potential is just so-called box-shaped. So it is it doesn't vanish only in finite region of x, say between minus a half and a half. And we will derive a certain equation for energy, which is E in this equation, for which the wave function found from this equation is normalizable. So again, in this case, the potential is as shown here. So it's 0 outside this interval and equal to minus u naught inside this interval. So let us see how to deal with that equation. So first step is to change the distance variable, and it's much more convenient to work with distances which are dimensionless. And in order to achieve that, let us slightly rearrange our differential equation. So the first step would be to multiply it by 2m of h bar squared and change the sign. And next, it is quite convenient to measure distances in units of, let us say, measure distances in units of a. So x equals z, which is dimensionless, times a. And then the equation written in terms of psi of z, psi of z, becomes and now it is convenient to introduce another dimensionless parameter which stays in the right hand side. So let it be kappa squared, and notice that the eigen levels of this equation will be negative, as the bound state in this problem can be only of negative energy. So it's convenient to denote this as kappa squared, having in mind that E is actually negative and the right hand side is positive. And next, what we have to do with this equation is to realize that it is convenient to solve it into three different segments of space. From now on, let us be interested only in the ground state wave function of this problem. And in this case, the wave function itself can be found as an even function of position. So for this, for discussion of this point, we refer you to the Landau and Lifshitz textbook, and you can find the reference in the description of this lecture of your course. But now let us concentrate on the solution which is even in independent variable x, and hence potentially corresponds to the ground state. In this situation, it's enough to look for the solution only on the half line, say from x equal 0 to infinity, and let us first divide the position domain into two regions, and for each of them let us write down the Schrödinger equation as it turns after substitution of u of z into this equation. So for example, in the simplest case of region 2, the potential vanishes and the equation becomes psi double prime equals to kappa squared psi. And this solution, this equation is very well familiar to you. And if we are looking for the normalizable wave function, then we need to write that psi equals some arbitrary constant c, which still to be found, times exponent of minus kappa times x. So please note that this wave function in the region 2 has some arbitrary constant c, which still has to be found. And in addition, it has a parameter kappa inside, which depends on the energy on which the equation is solved. And in the part 1 of the position domain, the equation becomes different. And the main difference is that in the left-hand side, apart from the kinetic energy term, that is the second derivative of psi, there is an additional term, which is just and most crucially, all the change in the differential equation is simple, and it, in fact, can be rewritten in the following form. This equation is formally very similar to the previous one, but with one crucial difference. In fact, we understand that wave function in this situation should behave like that, with exponential decay outside the well, and it means that this solution inside the well is actually cosine-like, and this term in the square bracket has negative sign, so it is minus chi prime squared. And most importantly, inside the region 1, we now have to choose a proper solution of this equation, and we have, of course, cosine and sine-like solutions. And at this point, we need to involve our argument about evenness of the solution corresponding to the ground state. Hence, we need to write that psi equals to b times cosine k prime x. And this is one of the most crucial arguments of this story, which will be then transferred to a more complicated situation, is the following. We don't need to solve the differential equation on the whole axis. We actually need to solve it only on one semi-axis and then impose a certain boundary condition at x equals 0. And this boundary condition is dictated by the fact that either we're interested in the ground state, second excited state, etc., then wave function is an even one. And if we're interested in first excited state, a third excited state, then a wave function is odd one. And in this situation, as we're interested in the ground state, we need to pick the solution which is cosine-like. And in other words, the corresponding boundary condition can be written as psi prime at x equal to 0 is equal to 0. And this is this crucial ingredient which you just need to take with you. This ingredient is that instead of solving the equation on the whole axis, we just put the proper boundary condition. And for even wave function, this boundary condition is, of course, that derivative of the wave function should vanish at x equal to 0. So from now on, let us proceed and derive the exact spectral equation from which eigenenergies E can be found.